Charged Tape Lab by Colin Funkhauser. The purpose of this lab is to investigate contact charges as they present themselves on tape and to calculate roughly the amount of charge on a piece of tape using Newton's second law and Coulomb's law. A preview of the results is the charged tape pieces repel each other but are attracted to negatively charged objects, so the charged tape is positively charged. And the charged tape had a charge of 8.9 times 10 to the negative 9 coulombs. Some fundamental principles are Coulomb's law, which is force is equal to a constant times the charges over a distance squared. The electric force, which is the electric field times the charge of a particle. And Newton's second law, force is equal to mass times acceleration. Tape is modeled as a point charge, and each tape piece is assumed to have equal distribution of charge. The initial conditions, the system is defined as tape B, and the surroundings are tape A and the rest of the universe. So 2 pieces of neutral tape are placed on the base piece of tape and pulled off to charge them. Tape B is draped across a book, and tape A is held underneath until tape B moves. The distance was then measured and used to calculate the Coulombic force. The U-tapes repel each other, and the U-tape was attracted to a neutral object, so the U-tapes are positively charged due to the repulsion from the negative pin. Tape B moved when tape A was 0.00192 meters under tape B. The length of the tapes are 0.2 meters long with a mass of 2 times 10 to the negative 4 kilograms. The distance between the tape pieces was 0.00192 meters. The gravitational force was 2 times 10 to the negative 4 kilograms times 9.8 meters per second squared, which is 0.00196 newtons. And the electric force, which is equal and opposite to the gravitational force in this scenario, is 8.9 times 10 to the negative 9 coulombs. So the results are that electrons lost by the tape are 5.6 times 10 to the 10 electrons. The area of the tape is 0.0038 meters squared, and an area of an atom is 1 times 10 to the negative 20 meters squared. So there are 3.8 times 10 to the 17 atoms on a piece of tape. The ratio of electrons lost to atoms on this piece of tape is 1.47 times 10 to the negative 7. Looking at the computer model, modeling the gravitational force as well as the Coulombic force and creating objects to simulate the point charge interactions, it can be seen that the magnitude of the charge is 8.96 times 10 to the negative 9 coulombs, which is very similar to the experimental. The electron deficiency is 5.6 times 10 to the 10 and 7.14 times 10 to the 6 atoms per electron on the tape. The computational model of electron charge was 8.96, whereas the experimental model was 8.9, so very similar. And some sources of error would be treating the tape as a point charge instead of a full object, rounding errors, and possible discharges during tape manipulation. What if the electrons were positive and the protons were negative? If the charges were flipped, the same results would be observed because the like charges would still repel and the opposite charges would still attract. It's important to handle the tape as little as possible so that electrons have as little time as possible to transfer from the tape to other objects such as hands or books, which would influence the results of the experiment due to a unequal charge distribution compared to little manipulation. In conclusion, point charges can be used as a modeling tool in place of everyday objects, and the model will be relatively close. Newton's second law and Coulomb's law can be tested and proven using simple experiments like these, and charges are easily transferred from object to object.